All right, I think we'll get started. So thank you today for joining us, talking about keeping the hackers out in embedded security. Just a few points real quick. If at any time you have a question, feel free to pop it up in the Q&A chat. I'll try to keep an eye on that and answer those as we go. I'm very happy. This is intended to give you a good background on embedded security and give you some ideas. It's intended to start a conversation. So I'd love to I'm happy to stop at any point during the discussion, have a conversation, or even at the end have some good Q&A. But happy to have you all here. Thank you so much for joining me. So real quick, I'm Joe Schneider, family man, dad of 3 girls, and an amazing wife. Embedded software for 20 years, multiple agile transformations, and basically a passion for improving the state of the art. That is why I started Dojo 5 with a number of other awesome folks that do all kinds of firmware. We're focused on modernizing firmware in general, the whole life cycle, everything. Dojo is about learning, and 5 is about a foundation and family. I've got 5 in my family, and we wanted to make sure that we have rich and deep connections with our clients and basically anyone that we interact with, even the broader community in St. Paul, Minnesota. So real quick, the plan today, we're going to talk about some security concepts, hopefully give you a good idea of what those are, talk about some common security issues that we see either when we're implementing or helping out clients, or even just in the news. Then talk about a couple fails that are recent and just kind of interesting to talk about, and we can kind of walk through that. All right, so just getting started, evaluating your security. So the trick with security is it's a arms race to some degree. You can never have enough. And it all kind of depends on your risk, the impact, and the cost. And these are often business specific or specific to your need. Here I have a picture of a front door. You know, most of us have front doors. And of course, the trick is we most of us have locks on the front doors. But take a look at this front door. How would you get in? You know, I mean, if the lock's unlocked, great, you can just walk right in the door. But of course, if somebody's sufficiently motivated, they can just break the glass right next to the door. If you feel like it, you can reach around and unlock the door. But if you don't, you can just kick down the door too. So it kind of depends. What are your threats, and what's the risk that this is going to happen? What's the impact? I mean, if somebody really wanted to, you could have a door without a window there. But geez, if all it takes is a car or a bulldozer. Eventually you could have a wrecking ball. So like, if somebody's sufficiently motivated, they can get into your house. And I think the same applies for all embedded systems. And so you've got to decide, luckily, most people don't have, state level actor kind of money, but it is important to look at your risk, impact, and cost. That's typically how we evaluate security in a system. And the way that we evaluated is using a threat model. There are a number of threat models. I posted up CVSS there as a talking point, but there are many threat models. It's basically a framework to brainstorm, evaluate, and then document the security of your system. Better than just throwing things on a whiteboard. And a lot of these have very kind of defined ways to kind of walk through security. CVSS, which I threw down there, you can see there's a number of different metric groups that they have, and these help you kind of think through this whole risk, cost, impact formula, and for any given vulnerability that you come up with as a team as you're evaluating the security of your system, you can then kind of rank it and in a certain way to kind of help you decide what you're going to address and what types of mitigations you need in this case. So, and it kind of walks you through a number of different areas so that you don't forget any places. It kind of helps you avoid blind spots. So, and most of the threat models just provide different angles, different ways to kind of approach that. So, take a look at some of those models if you're not familiar with some of those models, and or hit me up afterwards if you're interested in learning a little bit more about them. But this is an important concept to modern security on devices. Then I kind of mentioned it already, but vulnerabilities and mitigations. Vulnerabilities, you'll hear that a lot in the security world. Basically any path to attack your business, and I kind of added in there, not just the device. Your attacks, as we've seen a lot in the web, as it's gotten more popular, and devices are starting to see this too, denial of service attack, which doesn't necessarily mean that they've like compromised your device. It just means that the device is not available to do the function it was supposed to do. And if it's playing the background music in your elevator, people might not notice. The impact's pretty low. And so then, it's a vulnerability that, it has a low impact. You may not have a concern about adding a mitigation for it. But in some cases, it could be a device that, keeps your car running or keeps the plane in the air or something. And so then it's a very critical. The impact could be multiple deaths. And so then you obviously need to have mitigation, if not multiple mitigations in place to prevent that. And a mitigation is just defines how you reduce the risk or impact to acceptable levels. And the acceptable level here is very dependent on your business and what it can accept, what it can tolerate. And then there's security architecture. And this is kind of just speaks more to kind of the high level in your company, in your business. How are you planning to document your security, and how are you going to build a security culture? The security plan, as I mentioned, should have documented assumptions, the vulnerabilities, and the mitigations. So it serves as a living, a written, kind of a testimony of what was discussed, what vulnerabilities were identified, and then what mitigations are in place, and then you can kind of build on it or refer back to it if, as the system is built, inevitably you learn things, things get more complicated than you thought, and now you need to head back to the assumptions to see if what you're building is within the security plan that as you intended initially, or update the security plan. A security culture is also another big thing. It's great to have a security plan, but if only one person knows about it, understands it, has read it, then it's very easy for the team, an individual contributor to just write a small piece of code that violates that or adds a little hole or vulnerability into the system that's not mitigated, and all of a sudden you've got a big problem. And all it takes is one person to figure that out, and they can spread it very easily with the internet, and your system is toast. So making sure that you have a security culture where it's defined, where it's shared, and making sure it gets implemented early on in the project is really important. All right, some other kind of like more detailed concepts. So encryption. In general, and I think a lot of people understand what encryption is, but I kind of bring it up just to kind of juxtapose it against some other concepts. Encryption, of course, is hiding data in a way that only the intended receiver can view the information. So it's all about secrecy. Like, this piece of information needs to be secret. We use it a lot in healthcare type of devices where protected health information, PHI, needs to be protected by law. And in some cases, we use it for other reasons, privacy, and so, banking data, all kinds of things. But it is really all about the secrecy, whereas authenticity is where the data might not be secret, but you can verify that the sender was authentic. And basically, we know that this message that came from somebody, even though people could have sniffed it, could have heard it, we know that it actually was, this person X that was intending to send it. Typically, hashes or signatures, if you've heard of those terms, are used for the authenticity piece, whereas encryption is, more using a specific cipher. You don't always need encryption is the real quick point here. And then, EIR, BIS, which is basically export controls in the US, and there are others globally that regulate encryption much more heavily than they do regulate authenticity. So you can actually, if you design too much encryption into your device, it may not only be overkill, but it might also prevent your device from traveling overseas, and it might require you to rework stuff. So good, just some interesting information on implementing security there. And then another good concept to think about too is authority versus authentication. So authority is all about what a given user is allowed to do in their access level. But it's not necessarily, do we know who they are? It's just about what they do. So, and then authentication is really all about determining who a user is. And it's valuable to think about those two concepts separately. Often they require different strategies, and often they are different modules in your software. There is often one authentication piece that identifies who is this person. And once we've identified who that person is, then they get all the authority of that particular user. And so there's this principle of least authority. And so the idea being that when you design your system, if you have multiple users or multiple roles that can be played within your system, making sure that each function in your embedded system only has the authority that it needs to get the job done that it's doing is very important. You'll see this in Linux class systems, multiple users will be running, and maybe a particular function of the devices to manage the database. And so maybe you've got a little embedded database. And so in that case, we don't want that user to be root or to have access to the entire system. We want that user to be locked down so that they really only can access the database. If that user is compromised, then that compromise only gains the authority of that user, not the authority of the entire system. And so then, yes, it's probably in a compromise. It's partially compromised, but often it can limit the surface of the attack greatly. They might be able to destroy the database on one device, but they don't have a path back to get to the entire device and therefore the entire fleet of devices or something. Another concept that you may have heard is man in the middle. So in this case, Alice wants to talk to Bob down there in the corner, and Mallory finds some way to be in the middle. Often it happens as Alice and Bob are setting up the phone call. It usually doesn't happen in the middle of a phone call or this virtual phone call. And so there are a number of different solutions, whether it's certificates or whether it's other kinds of key exchanges that prevent a man-in-the-middle attack. But what ends up happening here, the vulnerability here is that when if Mallory is able to get herself in the middle, she can pretend to be Bob to Alice, and Alice thinks she's talking to Bob, but she's actually talking to Mallory. Not only does Mallory have visibility into what Alice and Bob are talking about, but she can also inject false information, change the information going between them. So it's a pretty big vulnerability and one that's easy to forget. You can add encryption, and if you don't have a secure key exchange or whatever, then Mallory can very easily get in the middle, and it can be a big deal. And then with embedded systems, there's also this kind of concept of physical attacks. It requires access to the device, things like power glitching, where you may have locked down your silicon and written like some protection bits or something so that the device can't be read in the field, which is a little bit of security by obscurity, as we'll talk about in a sec. But if you've got stuff in the chip, I hope it's not secrets, because people can get that pretty easily. But power glitching is one fairly low cost method that's been gaining popularity with availability of low cost FPGAs and some other tools that allow you to do the timing that's required for power glitching very repeatably. And then in many cases, and in one case even very recently with the Nordic chips, a very popular Bluetooth chip, a guy was able to glitch the devices and read out the full firmware read for Logitech mouse. And so power glitching is a way for folks to get into the silicon and read your data. The JTAG or debug access is another way. It's easy to turn those off, but actually the power glitching story from above was one case where that access was re-enabled via power glitching. And once they have that, they can do a number of things. View memory as the device is running. They can inject new code, and maybe that's no big deal. Maybe it is. Depends on your business. And they can add breakpoints, start to learn more about how your system works. So. And then serial port access, another thing that we tend to need as developers when we're developing these things, to have some kind of, serial log or terminal or command line interface on the devices. And when these devices are put into production, it's often really nice for testing to have that serial port access too. But if a hacker or somebody that's trying to get into your system finds that serial port access, it's really easy for them to, depending on how you've protected it or mitigated this risk, then it's really easy for them to get in and possibly wreak havoc on the functionality of the device or even the functionality of the broader fleet of devices in general. All right, so that kind of covers some concepts that I wanted to cover in security. Now, just talking about some common security issues, and just talk through what that means for embedded devices. So one big one that we have run into several times is that you get folks who know a little bit about encryption and security, but not a lot. Embedded devices tends to be a little bit of a wild west for these folks. They know they've never had a fleet of devices before, and there are a number of different solutions out there. And so they convince themselves they want to roll their own encryption. And that is a very bad idea. There are so many good, usually you don't need to get too fancy to get something that's very solid. We've had SSL, for a number of years now on the web, and that is pretty strong. Hasn't always been strong. There have been, vulnerabilities in it, and we've learned as we've gone. But like SSL often does the trick for most things that we're working on. But there are some cases where you need to encrypt things in a different way than SSL is typically able to do, and that's where you might be tempted to roll your own. I just threw up a couple of examples that happen to do with Bluetooth. There's a zillion of them that are happening. I mean, one of them was literally last month and a half ago here. But there are plenty of examples of encryption done wrong on devices that, in very subtle ways, that can then lead to a complete breakout. Even things such as the compute time that's needed to run a random number generator, and then viewing the power of a chip while it's in operation, and suddenly you can start to learn information about like what state the random number generator might be in, and then all of a sudden you've compromised the RNG that's feeding a crypto algorithm, and now all of a sudden you've compromised the crypto algorithm, and it's there's very subtle ways to do it. So yeah, and people then have learned from this and then hardened it. Harden their encryption algorithms like to these issues. So rolling your own, bad idea. SSL I mentioned before, but SSL without certs is also a pretty bad idea. It basically opens them up to man in the middle. SSL will build a nice encrypted connection for you. But if you don't add certs and you turn off the certification checking or the certificate checking, which is really tempting to do in a lot of cases when you're developing, and then you forget to add it. It can add to basically you're wide open for man-in-the-middle attacks. And as I mentioned, it's tempting, especially on embedded systems, not to use them. They're often require a number of additional steps. They're big. They can be big. Self-signed certificates are one way to avoid them being too big. But they typically take a lot of RAM and flash, and some little micros can't even really, might be able to do SSL in a very small environment, but in a big environment, or I'm sorry, with a very large micro, but in a very small micro, it may just not be possible. It does require some RAM and some flash, so make sure you design for that as well. Default passwords are another big way that things get compromised. Again, very, very easy to do. As I mentioned, this is kind of this anti-pattern of security through obscurity. If your security is all about, we're going to hide the key under the doormat, and we're going to hope nobody's going to look under the doormat, you're in trouble. Because yeah, you know, in the doormat example, if it were an actual person walking around doormats, yeah, in most cases they're not going to find it. But when we're talking about electronic devices, all you do is you write up a script and you have it check every single doormat on every single device on the entire internet. And very quickly, if you have hid your key under the doormat, it's going to get found. It's tempting, you know, for automated testing, ease of production. In this day and age, it is just not something you can do. FDA will not approve your device if it has a default password of any kind. And so there are even, you know, a lot of the approving boards are starting to wake up to this too, of just like, hey, there's too many ways to compromise things if we have default passwords. It needs to be from the manufacturing, you know, from manufacturing, it needs to be able to have a unique device. And you can either do that through provisioning, or you can do it through having a, you know, unique devices programmed at the factory. But it needs to be that level at this point. Anything less is easily compromised and a security risk. Then OTA updates. There's two on OTA updates actually, but don't implement OTA updates without authenticity checks. That basically means, you know, regardless of whether you decide that the OTA update itself needs to be encrypted, because there's plenty of reasons why in a lot of cases it doesn't need to be. It's not secret what the firmware is. You just want to make sure that nobody else loads on their own firmware that's malicious. I mean, you can imagine an internet connected appliance of some kind in your house, and you know, it's very tempting to find a way, you know, for hackers, and very bad PR for, you know, appliance manufacturers, for them to, you know, for somebody to find a way to sideload, you know, something onto those devices, and get them to do something that they shouldn't be doing. You know, it can sleep for a while and operate normally, and all of a sudden, you know, do something bad. I mean, and in some cases, if you're talking about machinery, it could do something that could harm, you know, individuals or property. So it can have some pretty big impacts. You know, you can decide, I guess I mentioned whether encryption is important or not, but absolutely, in this case, authenticity means that, you know, there's some kind of key that is checked on the device, or some kind of signature. A lot of times public-private key is used in this case, and that's a concept I didn't go into, but where the private key is held by the company, and a public key can then be distributed to all the devices. You need the private key to sign and come up with a cryptographic hash on your update package. But without that private key, nobody else can come up with a signature that works. And then through amazing mathematics, the public key that's on all of these devices can be used to check to see whether it's a valid update file. And if it is, great, then it performs the reprogram. If it isn't, then it can reject it. And even if somebody, you know, digs into your firmware, figures out the public key, they really have gained nothing. They cannot use the public key to sign new OTA updates. They only can use the private keys. And then just more in general on OTA updates, don't leave out OTA updates entirely if you can. OTA updates are becoming more and more important. If you've got anything that's connected to the internet, I'd say, and even if it's connected through Bluetooth or through some other kind of LoRaWAN or Cat-M or anything, I mean, those devices really need to have a way to be updated. FOTA updates for cellular modems are required by the carriers. So you're not going to be able to ship a device that's cellular without having that update capability, at least for your modem. And you almost certainly want over-the-air updates for your application code as well. And it's most of silicon manufacturers will provide an over-the-air update capability and reference design. I'll say that that's usually about 20 to 30% of the way there of where you actually need to be by the end of things. So there's a lot of, don't underestimate the work in implementing that. Don't just kind of check a box saying, oh, we got OT updates, because it can be something that folks are tended to leave out, are tempted to leave out at the end of a development cycle where they've ran out of time or ran out of money. and it's something that they've left till the end and end up cutting scope, I don't think it's a good idea. As in fact, for our clients, we typically advise it's one of the first things they do, because it not only does it add a security mitigation, but it also provides a lot of opportunities for development to ease the development cycle as well. And there are just vulnerabilities that are found all the time in embedded systems. If you ship a device that doesn't have an updated capability and you find out it has a vulnerability, there's nothing you can do. And then there's another class of security issues all around brute force. So let's say you do have some kind of unique device password on your serial port. Great. If I can just code up a little script and hook it up to a Raspberry Pi or something that's just like running all of these, great. Then I don't know if it's not sufficiently long, I might be able to figure it out in a weekend. And if I've broken into one, maybe I'll learn something from that about some other security vulnerability in your system, and now I can break into any of them very quickly. And now, or I can discover other vulnerabilities that will let me in easier. So don't forget about brute force. This is also why when my 1-year-old starts playing with my phone and entering bad passwords, eventually it starts locking her out, right? It's a timeout implementation where it says like, oh, okay, well, you've tried 5 times, you got it wrong all 5. So I'm gonna make you wait another minute or 2 before you can try again. And this will typically sufficiently mitigates a brute force attack. Yeah, so they're pretty easy to mitigate, but also at the same time, it's often something that can get overlooked. So then I'd like to talk about just a couple of fails that are recent, and maybe even hear about a few from you guys too. One fail recently, there's this good old Wink Hub. It's a IoT gateway for your system. This is, and these are good cases because they're cases where they tried to do the right thing, but then they kind of failed in their execution of it. So the Wink Hub is a IoT gateway device that it connects up to lights and other things, I think over Zigbee and maybe a few other wireless options, but it had a SSL connection to the mothership, and it had a certificate and certificate chain as they should have. So hey, they did everything right? Well, not quite. They forgot to. So when you sign a certificate with the SSL certificate chains, every certificate has an expiration date. Or you should have them have expiration dates. In this case, they had an expiration date and somebody forgot and dropped the ball. The certificate expired in the field and before they got updates to all the devices. And then what happens, of course, is then the devices did not connect to the mothership anymore. They were not able to connect to the cloud. It's basically becomes the same as a man-in-the-middle attack. It appears as if it's a man-in-the-middle attack occurring to the device, and so it rejected the connections to the cloud. Thought there was somebody in the middle trying to inject itself. The CA failed, and the Wink Hub was not able to connect, and so people had to mail it in and get it fixed, unfortunately. Another one that I'll mention is kind of frequent or kind of recent is the Samsung Blu-rays. I don't know, that's actually an LG Blu-ray device, but anyway, it was the Samsung guys had a little issue fairly recently that was in the news where there was an XML config file inside of the device, and the device had over-the-air updates, and it would, if you connected it to the internet, it would check in with the mothership and grab XML config files. If the XML what happened, unfortunately, is that there was a number of elements in that XML file, one of which was a list of things. And in their latest update, they decided, oh, we don't need anything in this list anymore. So they reduced the size of the list to 0. It was properly formatted XML, but something in their code could not handle an empty list there. And so the XML, and what happened was on reboot after updating that file, it would look into the XML, and the processing that crashed would happen there. It would process the XML. It would see an empty list, crash, and then it would go into a reboot. Unfortunately, the step where it checked for new XML files is after the point at which it was crashing and reading the XML. So it has, at this point, the devices were boot looping. They were just, reading XML, crashing, booting, reading XML, crashing, and there's no opportunity, unfortunately, at this point, to upgrade those devices remotely. They just weren't even to the step where they were checking the internet yet. And so there's all these subtle ways, I think, for security to fail, even when you think you're doing the right thing. And in this case, unfortunately, their updates, it requires them to have the devices repaired by hand. Somebody has to open up the device, delete that XML file off of the flash, and or maybe possibly replace it with a new one, and then get it out. So unfortunately, it's easy to screw this stuff up. And with that, I mean, I just kind of wanted to get the conversation started here about embedded security and some common fails and some common ideas. I'd be really interested to hear any questions, any thoughts about what you have seen in the security realm of things. Well, and I mean, I guess if there aren't any questions, always feel free to reach out. My name and email are out here. And it'd be always happy to talk about security. It's definitely something that we see folks struggling with on embedded projects. And yeah, happy to continue the conversation online, LinkedIn, Twitter, or wherever you'd like. So we'll end it here then. Thanks so much, folks, for attending and having a good conversation about security on embedded systems. Have a great day.